Today we have the PhD thesis defense by Zhifeng Jiang. We will first have the candidates speak for 40 minutes, and then we'll open up the floor for questions from audience, if any. And then we'll have a closed session for committee members. All right, let's start.
Okay, thanks for your introduction, and thanks for your patience again. I'm Zhifeng Jiang. I'm PhD student supervised Professor Wei Wang, and welcome to my PhD thesis defense. And today I'm glad to share you how I can achieve private and efficient federated learning systems in a cross-device scenarios. So nowadays there are a lot of user devices on the edge, like smartphones or AI cameras. So these devices interact with us and generate massive amount of data. And in fact, these devices are also becoming very efficient. For example, smartphones can nowadays do model inference in just tens of milliseconds. So these available data and computing resources are drawing machine learning to the edge. Well, while learning on the edge can be promising, the data involved is highly sensitive and can be stored in several locations. So that is where federated learning or FL comes in. So FL is a technique to train a model using decentralized data without directly communicating them. So in FL, you start with the model at the server, deploy it to participating clients, and next, each client just train the model locally using its own data, producing a local model update. And next, the server will aggregate all the local updates, summing up them, and produce a global model update, and use it to refine the original model. So that is a training run in FL, and by repeating it over and over, you will finally get a model intelligence from different clients, but without ever transmitting the data. So actually, a real application like this is Google's Keyboard, where FL is used to train the next word prediction model based on user interactions to help users type faster. And in fact, FL is also widely used in other machine learning applications on the edge. But actually, simply keeping data on-site isn't sufficient for privacy. For example, as previous work points out, actually a QA server can actually recover a client training image in high fidelity by only using the local model update uploaded by the server. So we actually additionally need secure aggregation where it's still the server who computes the sum of local updates, but now we can't see each individual of them. And actually, this is still not enough because the global model update may still leak some sensitive information. Actually, the use of participant data can actually leave a footprint in it. So we additionally need to conceal somehow to perturb the global model update. So that is where we use differential privacy or DP, where we add some random noise to it to make the global model update, to make the footprint there blurry and hard to be exploited by the server. So in practice, the noise is added in a collaborative manner where for each run, each client will add an even share of the noise to this local model update. And so that after aggregation, the global model update will contain the exact amount of the target noise. So far so good. It seems that we have all the necessary components for private learning on the edge. And but however, these components typically aren't perfect, and neither do the way they interact with each other. So these issues all call for research that help us to generally improve the current FL systems. And my efforts into these issues is twofold. So first, I will look at the existing defense against the worst case attackers. I will resolve their problem to generally make FL more privacy preserving. And next, I will also look into the system optimization, where the goal is to reduce the time to accuracy. That is, given the target model accuracy, I will optimize the training so that the training can make it achieve the accuracy using as little time as possible. So first, let's look into my first work, Thesis, which aims to resolve the straggler effects for maximum efficiency. So in common FL practice, FL is typically runs in a synchronous manner, where for each run, the server has to wait for all participants to finish before it can aggregate their local updates and move on to the next run. And as you can imagine, in such a scenario, the training time will be bottlenecked by the clients who are exceptionally slow. That's what we call the straggler. So in fact, because there will be a large speed disparity in clients in FL, So for each round, you may encounter a straggler. So actually, according to our profile results, these straggler will have to force others to wait for its completion, and such idle waiting time can actually take at least or up to 57% of the total training span, which is quite substantial. So to solve this problem, one potential way is to just have fast client to join, possibly reducing the average runtime. And actually, this is not enough because client's data quality are actually also vary a lot. So your selected fast client may not have enough good data. And in that case, it may take you more training rounds to reach the target accuracy. So you may not necessarily end up with a shorter time to accuracy. So actually, it seems that a better solution should be consider both client speed and data quality. And this actually has been considered by an existing work, like the state of the art is odds. So odds, based on some profile metrics, odds will first rank each client based on the score that jointly consider in speed and data quality. And next, it will favor those clients who have high score in terms of participant selection, hoping to selecting those clients who have high speed and also high data quality. However, while this idea looks clear and cool, actually it cannot deal with some practical case, like when the speed and data quality are inversely correlated. So note that this case is actually not uncommon because high quality data tend to be large in volume and thus should need longer time to train. So in this case, we actually find that the odd cannot achieve the best of the two, and it has to bias towards the client speed, and meaning that the majority of participants is select at high speed but low data quality. So actually, such bias makes it fail to reduce the time to accuracy metric. In fact, compared to random selection, the most naive algorithm for participant selection, it actually will be even 2.7 times lower than random selection. So which is in fact very surprising. So actually, we argue that odd is not at all. So long as we have to consider client speed and data quality together, there should be no single heuristic that can fit all possible correlations of client's data speed, quality and speed. So that is where we need why we need a new FL training framework, Thesis. So Thesis still wants to tackle the straggler effects in FL for maximum efficiency, and actually it approaches it in a different way. It actually makes a case for asynchronous training, and so unlike synchronous training, asynchronous training can sidestep the tricky trade-off between client speed and data quality. And as you can imagine, such transition of training mode can actually bring some side effects, unexpected, but actually Thesis has a way of minimizing it. So as a result, Thesis can give you very promising theoretical guarantees in terms of conversion speed, and also it can have very superior efficiency over the existing synchronous methods. And what's more, the way we implement Thesis can be seamlessly ported to existing frameworks. So let me delve into it. So I mentioned asynchronous training, but what is it? Actually, compared to synchronous training, it has two additional features. So first, so after some clients finish their local training, the server can eagerly aggregate their local updates and produce a new global model without waiting for other running participants. And what's more, these new global model can be immediately sent to existing available clients for new round of training. So as you can imagine, with these two additional degrees of freedom, asynchronous training can actually allow slow clients to join. It can actually tolerate slow clients to join, meaning that in participant production, we no longer need to worry about system speed. We only need to focus on selecting participants who have high data quality, and no trade-off to make anymore. But again, as I mentioned, asynchronous training does come with some side effect. If not handled properly, it can bring some, it may counteract the existing benefits. So in naive implementation of asynchronous training, when if some clients miss the aggregation attempt, they can simply skip it and contribute to a later one. However, in FL, because client speed can vary a lot, it means that some clients may just skip too many aggregation attempts. So their contribution finally will be not as useful or even harmful to the current global model, because their local updates are based on an outdated version of the global model, which may have deviated a lot from the current one. In the literature, such local updates are referred to being stealth. So it seems that we do not only need to do asynchronous training, but also needs to limit the extent to which clients local update gets stealth. So actually, this can be done by controlling the aggregation pace, especially by forcing the aggregation in a way such that, especially when the stealthness of some local updates is projected to exceed certain limits. For example, to ensure a stealthness bound of 2, actually we need to pause the aggregation pace in a way such that any client, especially the slowest one, will miss at most 2 aggregation attempts. So actually, this idea has been explored by existing work in the context of traditional distributed learning, and its name is called stealth synchronous parallel, or SSP. But actually, SSP is suboptimal in the context of FL, because in FL, client speed can vary a lot, and we actually need a more nuanced method for maximum client efficiency. So for example, again, suppose that we want to achieve a stealthness bounds of 2, and actually with SSP, it only guarantees that there are at most 2 aggregation attempts being performed during the training of any client. But actually, it imposes no restrictions on when should these aggregation being scheduled. So should they be scheduled too early, then there will be actually long time for pausing later. So possibly missing the opportunity of involving more potential clients' contribution. So that is what I mean low client efficiency. So actually, we do want to enforce a stealthness bound for all of the updates during the training, but now we also want to control the aggregation pace control to be aware of client speed for maximum client efficiency. So to that end, we actually focus on the speed of the slowest client. Actually, based on the estimated training latency of the slowest client, we will evenly distribute the aggregation attempts. So that means now we will not aggregate. We will not perform all the aggregation even if some local updates are available until the scheduled time aggregation comes. And in fact, in practice, the identity of the slowest client can change as new clients come in. So in that context, when we schedule the next aggregation attempts, we are consistently referring to those who are currently the slowest. So actually, this new method for controlling the aggregation pace not only improves the client efficiency intuitively, but also can still strictly bound the staleness of any local updates occurring during the training. And this further allows us to derive a very nice property in terms of the convergence speeds of our asynchronous training. In fact, in the design of Thesis, we actually also consider some practical issues, and you may refer to the paper for more details. As for evaluation, actually, we assess the time to accuracy performance, which is our ultimate goal. Here, our baseline is, of course, alt the state-of-the-art synchronous method, which optimizes the participant selection process, but has to deal with the tricky trade-off between client speed and data quality. Here, we actually use 4 different alpha flows without loss of generality, and the results shows that Thesis, by being asynchronous and with some side effect well addressed, actually outperform alt by being at most 2 times faster. And what's more, if you further look into the communication aspect, you will find that the time improvement of Thesis overall actually comes at nearly no cost in terms of network communication, so which is desirable. To sum up, we have actually proposed Thesis, a new FL framework for mitigating the straggling effects for maximum efficiency. It can give us a promising theoretical guarantee. It can also show a very promising efficiency improvement over existing methods. And what's more, it has already been integrated to some existing production frameworks like Level. Next, let's talk about Thesis, another work that focuses on the 2 other components for private learning on the edge. So first component is about segregation. Again, as I mentioned, segregation allows the server to compute the sum of some local updates, but without seeing each individual of them. But how does it work? Actually, each participant will just start talking with each other and agree on with some, and each pair of them will agree on some specific random number. And actually, later, before uploading its local updates, each participant will apply all the random numbers it agrees on with others, either by addition or by subtraction, in a way such that After aggregation, all such random numbers can be cancelled out, leaving the global update in the clear. Actually, in practice, chances are that some plans may quit after the agreement phase, but before the aggregation phase. So in that case, some random number may just can't be cancelled out, and so the server can no longer see the global update. So to solve this problem, actually, in segregation, each random number is not only known by the two clients who establish it, but also backup in some way among other clients. So here, the point I actually want to make is that segregation actually relies on two cryptographic primitives. One is pairwise masking, and the other is secret sharing. And actually, both primitives can need to involve all participants in an all-to-all manner. So that will actually lead to some huge burden in terms of the communication and computation to FL training. Actually, according to our profile results, when you look at the training time all around, you will find that the operations time related to segregation will be actually at least 91%, so which is quite substantial. To solve this problem, indeed, in the literature, we have some work looking into it and proposing new algorithms for doing segregation. Hopefully, can make it more efficient. Actually, they managed to reduce the time, the theoretical guarantee, meaning that their performance gain can actually be somehow substantial if the problem scale is large enough, like if we have sufficiently many participants. However, in FL, we do not have too many participants, because even if we can have thousands to millions of client devices on the edge, but the actual number for participants in a realm is actually limited to only tens to hundreds. So that means in practice, in common FL practice, the performance gain of such new algorithm will not be too major, as you can observe here. But we still want a much faster version of segregation. So another component that Thesis look into is differential privacy. Again, as I mentioned, differential privacy let us add some random noise to the global model update to make any data footprint data blurry and how to be exploited by the server. So in practice, the noise is added in a collaborative manner where each client just add an even share of the noise, so that the only thing presented to the server will be the global model update protected by exactly the target DP noise. But as you can imagine, such way of noise addition is actually vulnerable to client dropout. So in FL, client can actually drop out for a number of reasons. It can run out of battery, you may lose the internet access, or it may just be occupied by some user activities. So the more clients drop out halfway, the less noise will be remaining in the global model update. So this will let the server see a clearer footprint of the remaining participants' data, which hurts their privacy. And even worse, so client dropout is actually not specific to just one single run. So during the entire training, it can happen frequently and severely. So meaning that the cumulative impact of such client dropout to the client's privacy will be actually substantial. So we do want to improve this problem fundamentally. So to that end, we propose Thesis, another new FL framework. So first, we want to make segregation more efficient. So to that end, we use system level optimization. And in fact, we, for the first time, introduced pipeline parallelism to FL, which indeed unlocks a large potential in system speed. And we also try to make DP more resilient to client dropout. And for that, we also propose a novel scheme for precisely control the target noise level in the global model update. And these together can be integrated seamlessly into Thesis. And let me introduce them one by one. So as for segregation, to make it faster, we actually consider fully utilize existing system resources. So that includes client communication resource, server communication resource, and server client communication resource. Further, if you look into the protocol of segregation, you will find that each step of it will be dominated by different types of resource. And if you further merge consecutive steps into that use the same resource into a stage, you will find that we can actually end up with 5 stages. Each adjacent pair of them, you just use different resource. So that actually brings us an opportunity to overlap the use of different resource by leveraging pipeline parallelism. As you may know, in the context of ML, this is not a new idea. In fact, pipeline parallelism has been explored in traditional ML, where data can be freely moved across different resources, each stage of a task can be assigned with a distinct resource. However, this is not the case in FL. So in FL, we can have some stages which have to be processed by the same resource due to the privacy concerns of data movement. So that means existing solution for pipeline parallelism in the traditional ML cannot be directly applicable to FL, and in FL we have to come up with our own solution with this new constraint additionally considered. So to that end, we do two things. We first enable pipeline parallelism in FL, and then we optimize it with the constraint also considered. So first, we enable pipeline parallelism. We just partition the original task of segregation into several subtasks. So that each subtask just aggregates a specific segment of the model so that they can be concurrently executed. Actually, the number of subtasks is left to be a decision variable to optimize, because we actually find that different numbers of subtasks can actually lead to different performance gain. And we do want to find out the optimal number of subtasks that can bring us the most performance gain. So this is actually done by solving math problem like this with, again, the particular constraint that I mentioned also well considered here. And you can refer to the paper for more details. And as for evaluation, actually, we can show its performance gain in various FL workflows covering different participants, scales, and also different model sizes. To be more realistic, we also look into different dropout situation, because that also plays a role in the runtime overhead. Actually, of course, here the baseline is chosen to be the original implementation of segregation, which just process each stage sequentially. So compared to such sequential execution, our pipeline solution can actually boost the performance generally in a general sense, and with the maximum speed being 2.4 times faster. Another good news is actually our pipeline solution is orthogonal to the specific algorithm of segregation. So that means we can also use it to accelerate other segregation algorithm like the secure aggregation class. Now let's move on to how Thesis deal with the differential privacy problem. So to maintain the target DP privacy, our first intuition is that the noise in the global update should not be insufficient at any time, even in the presence of client dropout. So that means each client should proactively add more noise than needed to withstand possible dropout. For example, in this 4-participant scenario, each client should add 1/3 of the target noise instead of 1/4, so that even if there's one client dropping out, the noise is still sufficient. But however, as you can see, if there's no client dropping out, some noise may be redundant and should be removed, or otherwise the precision of the global update can be hurt, and which in turn impair the final model accuracy. So to enable noise removal whenever necessary, at the very beginning, noise shouldn't be added in just one go. Instead, it should be decomposed into several components and be added separately. For example, here, each client, in the previous example, each client should add 1/4 and 1/12 of the target noise separately. So this way, if there's nobody dropping out and there's much more noise than needed, each remaining participant can just notify the server of the last noise component it used. And so that the server can subtract these noise components from the global update to reduce the noise level there. Actually, this is how we deal with this simple case. If we want to tolerate more clients to drop out, we actually need a more generalized solution. For example, this is what we should do if we want to tolerate up to 2 clients to drop out in the previous example. And a more rigorous closed form of the matter can be shown here. And actually, we prove that such noise enforcement scheme can precisely enforce the target noise in the global update in the presence of client dropout. And this even holds when the server acts maliciously, because we also have additional secure measures. Finally, as for the runtime overhead of doing so, we actually can show that the time overhead is no more than 34%, which turns out to be an acceptable cost to pay just for privacy. So somehow we actually propose Thesis, another new FL framework that can first make segregation more efficient and also make the differential privacy resilient to client dropout. Thank you. Together, I believe that these efforts can make the private learning on the edge more practical. Finally, let's talk about the my another word lotto, which do not just look into each or one single component, but it actually pays attention to the interaction of different components. Specifically, lotto actually examines the assumption made by segregation and DP, but not necessarily hold in FL. So again, as I mentioned, with segregation and DP, the only thing presented to the server should be the global mode update protected by just the target DP nodes. However, there could be dishonest participant in the population and who collude with the server. And they actually can choose not to add any noise to their local updates so that the server can see a clearer footprint of client's data. And even worse, if the proportion of dishonest participants exceeds a certain limit, segregation can directly fail. So that means the server can see much more things like a specific local update provided by nearly no noise. So it's desirable to have all the participants, or at least a significant proportion of them, to be honest. However, this may not hold in FL. So in FL, again, as I mentioned, right, there can be thousands to millions of client devices. Involving them all at a time will be not cost efficient. So rather, the server will only select a subset of them to join, and there are typically tens to hundreds of them. This will be done either by random sampling or choosing the best performing clients based on some client metrics like data speed or data quality or speed. So, however, a malicious server, if it is eager to breach the privacy of some clients, it can actually deviate from this process arbitrarily. It can instead intentionally select dishonest clients as many as possible to grow a dishonest majority. And this will break the security of segregation and DP. But there actually was no solution before. So we actually proposed Lotto, the first secure participant selection framework for FL. So it actually can work with a rather weak assumptions, like it does not assume any peer-to-peer network. It can work within the centralized network that is inherent to the FL scenarios. It can actually actually makes no assumption about the trusted third-party example of public key infrastructure. And this way, it can already support the basic random sampling logic and the more advanced informed selection algorithm. In either case, it can actually bring you some promising security guarantee in terms of preventing the server from arbitrary manipulation. Finally, moreover, the operational cost of Lotto is even mild or negligible. So let's talk about how we deal with random selection first. So suppose the current run index is 2. So what an only server will do is to first compute a random function for each client, with the C being the client's public key, and with the input being the current run index. And next, the server will select the client only when the corresponding output falls within a predefined range, like less than 3 here. As you can imagine, a malicious server can actually deviate arbitrarily from this behavior just to grow dishonest majority. So as you can imagine, a natural way for defending this process is to have clients in the loop. More specifically, for a client who is planning to participate, other participants should be able to verify whether its associated random number falls within the predefined range. Actually, the cost of doing so will not be too high because this only needs to take place within the participants, whose scale, as I mentioned, will not be too large. And this already uses a very nice property that is whoever a participant sees were not selected by manipulation, but only by chance. That is determined by the existing selection criteria. For example, in the previous example, if the range of the random function is 0, 10, then the corresponding selection chance for each client is just 3/10. However, this is why this is a good start. We actually need to take care of some practical issues before making it realistic. So first, what on earth happened to those all these clients who are not in the list, are they just associated with some illegal random number, or did they actually get ignored by the malicious server either before or after the computing the random functions? As you can imagine, either case, the server can actually grow its advantage in building dishonest cohorts. And so to solve this issue, we actually make honest participant additionally verify two things. So first, whether the list of the selection participant is large enough, and also whether the selection chance for each client indicated by the predefined selection range is more enough. So to understand it in a concrete example, let's consider a case where we demand a minimum of 200 participants, and also a selection chance no more than 0.1%. So with some simple algebra, you can know that with 99% probability, the proportion of dishonest participant will not exceed a half, meaning that the rest of the participants have to be selected from honest clients. So the server can never or cannot arbitrarily ignore the honest clients unless it has control like much more than 80,000 clients in the population, which we argue is not practical. So this is about the first challenge, and second challenge is actually server can now predict very precisely who will join for a specific round. So this will actually, because the inputs for random function are public and can be known well before the training. So this will actually enlarges the attack surface. Suppose that the server can know a specific client will join in a specific round, then before the training, the server can actually concentrate all its resources on compromising that client to make it to turn it into a dishonest one. So this will be much more efficient for the server than compromising random clients. So to mitigate such risk, we actually resort to verifiable random functions or VRF. So unlike common random function, and VRF is evaluated using someone's secret key, which is not intended to be released to the public. However, the evaluation of VRF still produces a proof with which someone holding the public key can verify the correctness of these outputs. So now with VRFs, we can have each client self-determines the participation qualification of itself using its secret key. So the result will be no longer predictable for the server, but still being verifiable for the clients. So the final challenge is about like, even if we can have a very perfect participant list, like there is an honest majority, how can we ensure it throughout the training? You know, currently nothing can prevent the server from including non-selected dishonest client or disregarding selected honest clients. So fortunately, the security property of segregation can be leveraged to solve this problem. So first, in secure aggregation, each participant will only we will share anything necessary for running the protocol to all its peers it sees in the list only once, meaning that anyone involved later, especially those dishonest ones silently by the server, will not receive any meaningful input, so thereby imposing no privacy risk. And also in segregation, each participant will actually engage in a consistency check before letting the server know the global mode update. So with this check, each participant can actually know precisely how many clients in the list still engage. So that they can be alerted and abort if the server disregards too many honest participants. So that is basically how we deal with the random selection. And you may refer to the paper for more details. Finally, let's briefly talk about how we deal with the informed selection. So as I mentioned, an informed selection actually wants to select best performing clients based on some metrics. For example, the server may keep tracks of client speed just to find out the fastest clients for maximum efficiency. And again, a malicious server, of course, can deviate its desired behavior arbitrarily. And here, actually, the major challenge is while we can have verifiable randomness for random selection, we do not have verifiable client metric for informed selection. Because actually, first, the server can easily produce or use fake metrics, or it can actually, dishonest participant can even adjust themselves just to gain this process. So to make informed selection really secure, we argue that some randomness has to be introduced. So actually, we try to approximate each informed selection problem by random selection one. And due to the time limit, you can refer to the paper for more details. And so it's for evaluation expert looks into the security of lotto. So actually, either for random selection or informed selection, we have proven that if you use lotto for participant selection, then with high probability, the fraction of dishonest participants will be very close to the base rate of them in the population. So that means the server cannot arbitrarily throw the fractions of dishonest participants. To see in a concrete example, let's consider a case where we have 200,000 clients, where 0.5% are dishonest. In this case, if the target number of participants is 200, and then with some simple algebra, you will know that with certainty the server can populate any fraction of the participants with dishonest clients. And this just happens with 100% probability. However, if you use lotto, then the server must face an increasing difficulty in growing dishonest cohorts. For example, the success rate of having at least 10% of the participants being dishonest will be very close to zero. That is like 10 to the power minus 15. And actually, such security comes at nearly no cost in terms of performance. So actually, to show that we use different workflows and also cover different population scale. And if you first look in the time metric, which is related to the computation, you will find that the time cost will not be larger than 10%. And even better, if you look at the communication metric, that is the traffic induced in per run, you will find that Lotto's overhead is even negligible. Finally, we are also glad to share to you that the Lotto can function in the same or similar way as insecure selectors do. So here we again use Lotto, use ODD be our baseline. So ODD, as I mentioned, is the state-of-the-art informed selection algorithms which optimizes the metrics. And however, it can be easily manipulated by the server. So to assess how we achieve the comparable time to accuracy, we will first run all these FL frameworks with ODD being the selector, and then we will rerun it and to see if the time to accuracy performance match. And it turns out that the answer is yes. So that means while we have to use some approximation to secure the informed selection process, as I mentioned, these approximations can be still very highly effective. So to sum up, we actually propose Lotto a new FL algorithm for participant selection. It can actually work in the same or similar way as in secure 1.2, but actually it can provide you with very solid security guarantee and also minor performance overhead. So far I have talked about all the words contribute to my thesis. And I believe that these words can generally, when combined together, can generally improve the privacy and efficiency of existing FL systems in the cross-device scenarios. As for future work, I envision three possible directions. So first is about the incompatibility of my previous works. So as I show here, while Lotto and Thesis can get on well with each other, they cannot work with Thesis. This is because Lotto and Thesis actually are both based on segregation, and which requires that the identities of clients related to one global model update should be predictable by the server well before the training, which is not holding in asynchronous training as in Thesis. And so it will be very interesting to see how we can still protect each local updates without segregation in the context of asynchronous FL, or it is also interesting to see how we can still manage to relieve or mitigate its regular effects when during the use of segregation without asynchronous streaming. Next is about the privacy issue. So while we have made some progress in private learning on the edge, some privacy issue may still arise after the learning process. So one such example is that some edge users may require to undo the training after the training and just to eliminate the impact of the data on the training process, probably due to some privacy concerns. So in the literature, this is referred to as unlearning. And actually, we have also already seen some work in unlearning in the traditional ML, where we do see some successful attempts where we can eliminate the impact of some data on a trained model that has been released to the attacker. However, in FL, when some clients request to do unlearning, chances are that the intermediate computation results, like the global model update derived from the data, may already be released to the attacker. So it remains, or it becomes an open question whether it is possible or meaningful for doing unlearning in the context of FL. So finally, the final future work is about security. So long we have talked about much about privacy, and whose core idea is to conceal the individual contribution of each client. So this essentially raises another vulnerability that some malicious server user can exploit. So actually, there may be some malicious client who may want to tamper with the model utility by using some corrupted data to train and upload their local updates. So to preserve the model security at the server, actually we need to unpack each local update and do some sanity check. So as you can see, there exists a tension between enforcing client privacy and also achieving model security at the server end. And it is thus worth investigation how to reconcile the demands for both without sacrificing too much cost in other aspects like model fidelity or system efficiency. So I would like to conclude my PhD thesis defense. With that, thank you very much, and I'm glad to take any question.
Thank you.